My REU research is titled Unreal-Based Pose Error Measurement for AR-SLAM. My name is Maria Christenbury. My mentor is Ying Chen, and this research is conducted under Dr. Maria Gorlatova. For some software background, Unreal Engine 4 is the game engine which we use as our virtual real world. The scene we used in our research is depicted in the lower left-hand image. ORB-SLAM 2 has a sequence of images captured by a camera as the inputs, shown in the lower right corner, and the output is a constructed map of your environment and your camera's position and rotation, also known as the pose, depicted in the middle image. For the project's motivation, for every pose, there are 6 degrees of freedom, 3 from the position and 3 from the orientation. Our goal is to model this pose error of ORB-SLAM 2, since it would require very high-end equipment to model the pose in real life, which is inaccessible to most people. It's challenging to train and measure the performance of algorithms in the physical world because of limited scenes, a long training and running time, heavy manual labor, and the imprecision with measurements, since we don't have access to the ground truth in the real world. This is why our project connects ORB-SLAM with Unreal, so we can collect the error of the algorithm using virtual scenes with their ground truth. For the related work, the Edge-Assisted Mobile Semantic Visual SLAM paper explores EdgeSLAM, which is a SLAM software that uses an edge server to limit the computational resources required, designed for mobile devices. These researchers don't have ground truth data with the mobile phone, while we can easily access our ground truth, and they use inputs from their phone while we use inputs from Unreal. The visual appearance analysis of forest scenes from Monocular SLAM paper suggests using highly realistic game engines to provide the algorithm's ground truth data and more control over the camera. This connects to my research because we use a suggested photorealistic game engine, Unreal, as our inputs for our ORB-SLAM 2 analysis. The goal of our project is to measure and train the performance of the ORB-SLAM algorithm using Unreal Engine 4 and to calculate the error of the algorithm and make a model of this error using Unreal. The innovation of our project stems from exploiting the access to Unreal's ground truth of a pose to model the pose error. This is a diagram of what my project is. So the inputs for the SLAM algorithm are the snapshots of the scenes which come from Unreal. This algorithm returns the estimated pose, and in Unreal, we'll combine the estimated pose with the ground truth to get the pose error from the algorithm. For the implementation, we created blueprint code in Unreal to automatically move the camera and take high-resolution in-game snapshots. We created a depth map in Unreal. I converted the default file format from Unreal to match the tomb format using MATLAB code. We edited the default camera parameters for ORB-SLAM 2 to match those from Unreal. I ran our formatted inputs from Unreal in ORB-SLAM 2 and used the RPG trajectory evaluation software to obtain the pose error figures from ORB-SLAM 2. This image is the Y versus X trajectory graph in the ground plane, which has the X and Y coordinates of both the path the camera traveled in Unreal and the estimated path from ORB-SLAM 2 overlaid to visually depict the accuracy of the software. As you can see, ORB-SLAM 2 is overall very successful in estimating the pose of the camera. This next image is the Z versus X trajectory graph, which has the X and Z coordinates plotted for both the ground truth pose from Unreal and the estimated pose from ORB-SLAM 2. ORB-SLAM 2 was successful in predicting the translation pose of the camera in these coordinates as well. This final image shows the relative translation error plot, which has bar graphs depicting the variability in the ORB-SLAM 2 estimations compared to the ground truth. While this plot doesn't mean much on its own, when compared to the Y versus X trajectory graph, it's easy to see that the largest box plot corresponds to the point on the trajectory graph where the camera changes its path. This is also where the estimate and ground truth plots are the farthest apart from each other. This suggests that the software is at least accurate at estimating the pose when the camera path changes course unexpectedly. For my conclusions, I used Unreal Engine 4 as the simulator for the ORB-SLAM 2 algorithm to obtain the pose error of the algorithm. And we've concluded that Unreal is an effective simulator of a real-life scene to run ORB-SLAM 2, as well as ORB-SLAM 2 accurately analyzes the camera pose from feature-rich scenes in Unreal. For future applications of this research, we'd like to explore different trajectories for the camera in Unreal, different scenes, different SLAM algorithms, and different input formats, including stereo and RGBD. Thank you so much.